Hey everyone, how you doing? It's Clara and I'm back with another one of my science chats. So I talk to awesome scientists that I know, and today it's, as ever, it's a pleasure. I'm going to be chatting to Dr Dr Lia Li. She's a physicist, she's got her own company, she's CEO of a company, she works with quantum sensors at UCL. As a research fellow, just all around awesome person, really great. I think anyone that's watched this series have heard me talk about tigers. It's someone that I met through the tigers, and I'm very lucky to have done so in that regard. And yeah, with that, let's go and chat to Dr. Lia, shall we? So, hello Lia, and let's have another go. For the audience and those listening, we've just been chatting for 20 minutes and I wasn't recording it, and I feel like a big ol' dummy. So, hi, how are you? Who are you? And what do you do? Tell us a little bit about your work.
Hi everyone, my name is Leah and I'm a Royal Academy of Engineering Fellow at UCL, University College London. I work on quantum sensing using optical sensors. They involve taking glass spheres, glass discs, glass microspheres. We trap light in them and we see how motion affects the properties of the light. And we can measure displacement down to femtometers. You know, we're talking about 10,000 times smaller than a single atom, really sensitive. I'm also the director and founder of Zero Point Motion, which is a company developing optical inertial sensors. Inertial sensors are basically like the little chips inside your phone or inside your car that measure acceleration and rotation, basically motion, and they can track your position and help you navigate outdoors when you're using them with GPS. And we're hoping that our sensors are so sensitive that you don't need to rely on GPS all the time.
That'd be lovely, wouldn't it? Because the number of times GPS has told me that I'm in a hill or something. So,
Yeah, and also indoor navigation, like, oh, I
yeah.
can't wait to be able to help people actually like not get lost inside an airport and stuff, because I get lost like every time I'm in an airport, and it would be so cool to like download a map of the airport and then you just with your phone or with something else being able to like know where you're going in
That'd
real
be
time.
brilliant.
Be brilliant, wouldn't it? Yeah, I'm working on it.
Yeah. Oh no, that's great. And as someone that works a lot in the loves the outdoors a lot as well, and you lose. I mean, we try and work on maps, but sometimes the weather means you just get turned around um, in fog and things like that, and you
Yeah.
don't have signal. It'd be great to have something where it's like, well, at least we know where we are, and we're not gonna.
Yeah.
There was one time I'm thinking in particular where the weather was so bad it was before GPS, and we kept on finding ourselves right next to a big massive ravine, and it was like we didn't want to be next to that at that time because it was a bit windy. So that sounds brilliant. So we were talking a little bit, in the previous version. I'm like so paranoid now. I'm checking for the recording button, but it's definitely there now.
I can see it as well, so I'll
Good.
vouch for it. It's working.
We were talking a bit about, so you worked sort of in industry as well. So you did a physics degree, and then you worked in industry. And I was saying it's sort of a little bit different. I did an engineering degree, and then I worked for an industry as well. But I got involved in the science, and what I do now, I'm sort of a bit of both. But you were talking about your sort of journey, and even though you love physics, but you love the engineering side of it as well.
Yeah, so I did a physics undergraduate at Imperial College, and that was fantastic because I got to build lasers in my master's project, and that was
That's
the
pretty good.
time that I fell in love with lasers. I mean, I'm not gonna lie, I absolutely love lasers. Lasers are like my soulmate. I will work with lasers for the rest of my life. You'll probably have to bury me with a laser in my hand or something, because it was transformative for me to do that. Up until that point, you don't really get to use lasers in the way that the way that they're best used. You
Hmm.
kind of switch on something and you do something later or something like that. But in undergraduate labs, you never get to see what the insides of a laser are and how they get built, how they, that kind of fundamental side of things. And I was really lucky that I was able to build a laser from scratch. And I don't know what it was, but the power to make something laze was incredible. Like, I still to this day feel the confidence and the power in making something laze. I don't know how to describe it, but you're literally, there's a whole laser threshold thing, but there's literally a point where you turn up the power and suddenly you have a laser beam. And the fact that I made it was just like that set me up for life, honestly. So after that, unfortunately, not unfortunately, but this was my final year. I did a 4-year combined master's. So obviously there's a panic for your final year, like, where am I going to go? What job am I going to do? I was not confident to do a PhD at that point. So I managed to get onto a graduate scheme at BAE Systems, which is a defense company. And, everyone around me was so proud, because it was like, as soon as I graduated, I worked over summer in the same lab, because I did undergraduate summer research things because I was so keen. But then straight away, I went into industry. It was just kind of like, this moment that my parents were really proud of, because it was like, I done it. I did the whole, went to university, got a job. And there wasn't this like, big kind of break in between, if that makes sense. So I worked in defense, and that was really my first taste of engineering. Because you don't just do R&D in defense research. You don't just make something for the sake of making it. You're making it for an application or to improve something. So although every day I was working in a lab and doing effectively very similar experiments that I would do at university, the appetite for doing novel things wasn't quite there. So it was very kind of focused types of experiments. And I really missed that feeling I had at Imperial of kind of doing something really not unique, I guess, but just something that pushed the envelope a little bit. And I also felt like I had energy. I just had energy to kind of be a bit more risky in the science that I wanted to do. I felt like I didn't have to kind of align myself to like a 10-year project or anything. I wanted to be flexible and try some more riskier science projects. So I quit that job and went to UCL to do a quantum PhD, which was basically trying to make the largest macroscopic quantum object in the universe, which, now that I say it, just sounds really stupid. Why I even decided to do that PhD? Like, come on. I had to change my PhD title like 3 times, because it is not easy to get to the quantum ground state just like with anything. Like, it's
What do you mean? Just do it.
Just get there. Just turn on the experiment, right?
Yeah, just do it.
I got close to. I got cold, but not cold enough. But that was exactly the risk I wanted to take. I mean, I fully own the fact that I wanted to do something that would really stretch me to the limits. And the limit that I found was, with quantum experiments, you really do need a lot of resources and a lot of funding. It can't just be done on like this DIY funding type vibe of like, we're just beg, borrow and steal from bits and bobs. No, it needs to be a very well-planned, project managed year endeavor, with PhD students staying on as postdocs to have that continuity, to have that level of support. And unfortunately, my project was just a little bit too risky to really get to that final thing. And I work by myself as well. So, there's a limit to how much a single person can do this kind of thing. So I kind of went, had this engineering experience in industry. Then I went into deep physics again, like really deep physics. And then I wanted to stay in that sector. I wanted to stay around quantum technologies, but to do that as an independent researcher, or to do that with the conditions that I have, in that I don't want to leave the UK. I need to be close to my parents. It's just me and my parents in the UK. That's it. I'm not going to let that go and move all across the world to kind of work underneath other people. But it's hard to have ownership over postdoc work, because when you leave a group, you can't just bring an experiment with you. You start from scratch again. So I decided to pivot and to effectively go back to engineering and think about quantum technologies in a commercial viewpoint or in a prototyping kind of way. And then that led to me getting my Royal Academy of Engineering Fellowship, which is really to study this boundary between classical and quantum sensing, also in terms of application, feasibility of making products, much more application type focus rather than purely, I want to get to the quantum ground state because no one else has gotten there type vibe. And I really, really appreciated the fact that the RAN took, I consider it a risk because I'm not a part of the engineering community. You know, I'm a physicist, trying very hard to be accepted into a new community, and for them to see something in my application was really, really, really good for me as a person as well. And so since then, I very much consider myself an engineer. I want to do as good of a job as I can in representing engineering. And, you know, obviously I still love quantum physics and everything, but my future and my career, I'm just really happy that it's grounded in a new sense of drive. And with engineering, I find that it's much easier to have that link to society, to impact. I hate the word impact, but this kind of feeling of it's not just me that I'm doing this for, or it's not just, you know, a limited set of reasons why I'm doing this. You know, I do a lot of ED&I work, and, you know, with engineering, especially my company, I actually have a mechanism to help change things, either as an employer or as someone helping to shape the economy in some way. And I just felt that that was better suited for me than to remain kind of firmly in academia and think that, you know, and be limited to change through that system. Yeah.
Yeah, lots that I can pick up on, lots. And one thing about the, you know, the how you felt welcomed into engineering is something I want to come back onto later. I don't know if you realise, but you know, when you're talking about your own career, you're talking about grounded and energetic and aligning. And I'm thinking, you're using laser terms for yourself. You really do love lasers.
Oh man, I love lasers so much. Like
it's funny because I
have a lot of lasers at home as well, which I probably shouldn't. But anyway.
So I'm the departmental laser safety officer. So most of what I do with lasers is writing risk assessments or reading other people's risk assessments or telling people off. So I hate lasers. We have one in our lab, and when it works, it's good for what we do. But yeah, most of my laser time is paperwork.
Yeah, they're really temperamental, to be fair. Like lasers don't really behave right, especially the nice ones, the really nice ones of narrow line width, high power. Yeah, they barely behave. And yes, absolutely, laser safety is always a priority. I have a good trick for people if anyone does want a good trick. So when I used to work with lasers, I got into this habit of if you drop something on the floor, to always cover your eyes as you bend down to pick it up. And that's just a tip that I've told, because you'd be surprised how many times I see in labs people just not think about it. Because when you drop something, your immediate reaction is to pick it up. You don't think that there's a bench right next to you and that your eyes are going to get to bench height as you go down. Anyway, that's a really random tip. Sorry.
No, but that's a really good tip. And it wasn't one, mind you, I keep on making everyone enclose theirs or wear glasses. So.
Oh yeah, I mean, if they're enclosed and everything, then that's definitely the best.
Yeah,
you'd be surprised even now to this day, even if I'm not next to a laser, if I drop something, I'll always cover my eyes.
No, it's really good. It's a really good idea. I like it. Yeah. I'm quite lucky my one laser because we use it for deposition, so it's high power. It's but it's all enclosed, so it's cool.
Yeah.
I mean, we're using it for literally knocking off atoms of metal. You know, it's like. Yeah, they got some power to them, you know.
Awesome! I know they're really amazing things. They can do that, and they can also slow objects down. It's incredible how versatile they are.
Yeah, I like I said, there's loads that I could talk to you off the back of this. One one thing that I like is you talked about the sort of the fourth year practical, and you got to build a laser. Was the fourth year for you? Was it a taught one, or was it a year research in a lab?
Yeah, so I did, and I don't know if this still exists, I think it does, but I did what was called an MSci, which is a combined 4-year master's. So instead of doing a bachelor's and then you apply to do a master's separately, or one that's in a different field, I just did a straight 4-year kind of PhD course. And your final year, there is some taught elements, but it's kind of majority an extended kind of project, if that makes sense. You do a lab project for the majority of that year rather than only half of it, if that makes sense, for a normal bachelor's type finishing. So yeah, that was phenomenal, that experience. Not only was I mentored by an amazing female scientist called Dr. Gabriella Thomas. She now works for M Squared, the laser company. She taught me everything about aligning lasers, and she's first and foremost a friend, but also I consider her one of my greatest kind of mentors in life, because she was midway doing her PhD and she gave me an insight into that PhD experience that really prepared me, even though I wasn't going to do a PhD at that point because I was too scared to. I went into industry. Her words reverberated in my mind as I was thinking about leaving industry to come back and how to prepare myself, because she was very honest about what to expect, and also potentially what could be very bad experiences, but also she was a role model for me in terms of someone who was absolutely excellent at their technical skills, at the way that she understood the academic system. And also she was just so kind and nice, and she gave time to everyone, whether that was a cleaner, to a technician, to a visiting professor. I really learned through watching her the art and the beauty and the joy in just being a nice person. I'm to say that, but so many people don't want to use energy for that. It does take energy. If you're having a bad day, it takes energy to not take that out on every single person that you encounter in that day, if that makes sense. But it was really informative for me. I can't thank her enough. She's honestly one of the reasons why I felt confident enough to leave industry and do a PhD.
I fully agree about that being nice. It's just you're nice to everyone, because it's my philosophy as well. I'm nice to everyone. If I'm not nice to someone, there's a very
a valid reason.
You should always be polite to everyone. I love that message. Yeah, and I love that you're doing the sort of fourth year research project. So we do that in our department, and so most years I have 4 kind of master's students for a year. This year we've only got 2, just because of the world. But and I just think it's such a fantastic opportunity to really get your hands dirty, to learn about the practicalities of science, instead of going in without any experience into a PhD. And I think I'm not saying that taught masters aren't bad, but I think that the practical year is just such an amazing thing to have. I'm a huge fan of them. I just think they're brilliant. I really do. So it's cool that you're doing that. That you did one as well. It just picked up, and I'm like, yes. I just think they're so useful. I think they're just really good experience. Hopefully. And like you say, because when you go into a PhD, you've got 3-4 years, and you're doing it. And it's not for everyone. It just isn't for everyone. At least if you've spent a year in the lab experiencing real research and failure,
yes, constantly, yeah.
It prepares you, I think, for a PhD, and it'll give you a better idea of what a PhD is. So yeah, that's really interesting. And I think before you were saying that you were talking about quantum stuff, and you were saying that you didn't you understood it in a certain way when you did it for your degree, and that was a big part of why you wanted to get involved on a PhD, is to learn it from a different point of view and to understand it better. So what is it? I did an engineering degree. I don't know quantum, but I'm trying to actually make coatings for quantum devices at the minute. So I'm writing a project at the moment for that. I'm trying to get my
own.
Awesome.
Cool.
And for me, I need to know the coating side of it, but I still need to know the quantum. And quantum, you try and read up on it, and I don't know what it's like if you're being taught it, but it's flipping hard to just read up on.
Yeah. I think quantum is really hard because it's quite rigorous, if that makes sense, as in the foundations of quantum mechanics in terms of proving to yourself that certain rules are the foundational rules. Like there's certain things, I'm going to forget everything, by the way. I'm about to say a bunch of stuff that's like, everyone's going to be like, what is she talking about? But like there's all sorts of things to do with identities and stuff where you define something as something, as a matrix or as whatever, and there's lots of questions around, well, why? And so when you get taught, a lot of what you get taught are kind of the foundations of all these proofs. You just get taught all proofs of why things equal this and why that equals this and why this identity plus this equals this, why this operation times this equals this. And all of it is to kind of be like, so that you trust it. So you go, okay, I trust that that equals that. But it's not the same as like 1 + 1 = 2. It's not as easy as that type. It's a deeper level of trust. And I think for me, I just struggled because I don't consider myself particularly a maths person. That's not the language I speak when I do science. I think that's quite, I think I've kind of learned that about myself. But what I do like is experimental signals and the proof on the experimental side, not the proof on the foundational mathematical rigor side, but the proof that you see on a screen or in data that shows it on the data side. That's how I like to operate. So I don't particularly like thinking about things in abstract ways. You know, a lot of quantum physics, especially when you go into the equations like Hamiltonian, Schrodinger's equation, they're equations built on assumptions, built on very, very simplistic models. And they don't actually, to me, they don't look like anything that the experiment is actually doing. Because when I think about an experiment, I think of it as a systems engineering thing. There's software, hardware, there's noise and everything, there's process, and there's always environment. The environment is all around you, and that can produce really funny signals that look like the signals you want to measure. And so in a quantum equation, like a Hamiltonian, you don't have any of that nuance. You have this thing you want to measure in this quantum system will equal this signal. It doesn't take into account anything else that might happen. And so I think for me, I just view things much more on a systems engineering level. And what I wanted was to do an experiment where I understood how everything works together to then either generate or not generate your quantum signal, your quantum measurement. And whether or not I actually got to the quantum measurement didn't matter. The process of developing it all and problem solving and actually saying to myself, why is this not quantum, through the experiment, through the data, that to me, I felt much more in control, and I could, through that, learn all of this other kind of rigorous quantum stuff, if that makes sense. If I see on a piece of paper, this equals this, therefore this equals this, I'll just go, yeah, sure. Smarter than me came up with that. But if I build an experiment and I see a signal, the first thing I do is, right, how could this signal be trolling me? And actually, I've learned from experience, never trust anything the experiment says first time round until you check it a million times. Yeah. I've fallen for that before. I've like preemptively celebrated and like, you know, when you're like, hey, and then you go back to it and you're like, Oh, I'm so embarrassed. It's
Well,
like
well,
a
to be
loose
fair, there was a
cable.
pretty famous case of that a few years ago, right, where they got this impossible measurement and then they realised it was a cable that had fallen out. But
Yes,
they,
it's always a cable. It's always a cable or a microwave somewhere. If your lab is ever near like a staff kitchen, you can get them to take away the microwave because it's usually that as well.
oh, good to
And
know.
for me, I just felt that I as a scientist, I'm more rigorous as an experimentalist than I could ever be as a theorist. So if I want to prove to myself that I understand quantum mechanics, the way that I was going to do it, for me to feel confident, because I can revise and pass a quantum mechanics exam, but for me to actually truly feel like I have some understanding and expertise, I was going to gain that through the experiment side, that I knew that about myself. So yeah, that's kind of how I feel about learning quantum mechanics, and taking a bit longer to kind of become confident that you are an expert in this field. Yeah.
I'm definitely so I'm the same. I learned so much more through the experimental side of it. I could read a paper, but you read papers and you do pick up stuff, but it's not. It doesn't mean I've learned it. I have to do it. I have to do that experimental work, which is probably why I'm struggling so much just reading quantum for the first time properly. But so am I right? So you're using quantum sensors, and I guess this comes from just a lack of knowledge. But I mean, how are they working? Because I
Yeah.
think quantum, and I'm thinking, well, it's either this or this, and you're using them to figure out whether you're moving or not as sensors. Like, how does that work?
Yeah, so I think with quantum sensing, there's kind of a few levels of how quantum do you want to go. Yeah, I know, right? And the easiest one is you can take, let's say, a cantilever, a springboard, and because of Hooke's law and Newton's second law of motion, if this cantilever experiences forces like acceleration, it's going to deflect up or down because it has a stiffness to it, and you can model it as a 1D harmonic oscillator, our favorite oscillator. And obviously you have Newton's laws of motion. So if there's an acceleration, there's a force, there's an inertial force associated. And so that makes this spring go up and down proportional to the acceleration. You have a similar effect with rotation. If you've ever seen the giant pendulum in various science museums, they're free to swing in any direction, but you set it, you drive it in one direction, and then over the day you'll see that the pendulum starts to oscillate at angles. It starts to like rotate in its kind of oscillation, and that's due to a inertial force. It's due to something called the Coriolis effect, where the rate of rotation of the Earth rotating, will start to push the pendulum slightly off its axis and start to kind of pivot around effectively. So it's a really nice, simple mechanism because it's literally, test mass on a spring, that kind of stuff. Okay, so to make it quantum, there's first thing you can do is let's take a laser and let's shine the laser off of this cantilever. So maybe you put a mirror on the cantilever to make it a bit more nicer. So if you're shining a laser onto the cantilever and it's moving up and down, it's imparting a phase shift to the photons. So the photons hit it upon reflection. There's a phase shift added, but because the mirror is in motion, you basically have a differing amount. So it's kind of, the mirror's moving and the photons are being reflected, but the mirror is imparting a force as well that's making that shift different. And so what you can do is you can use any old light. You can use like classical light, like a diode, or like, even sunlight, for example. But the photons of that light beam are kind of spread in color that have different wavelengths. It'll be kind of what we call not very coherent, if that makes sense. And the beam itself might be quite big and ugly, and you might lose some of your light because it's kind of going everywhere. So now if you take that light source and you make it a quantum light source. And all that means is that you remove any kind of classical fluctuation. So there's fluctuations in the intensity of the light. If you remove all of the sources of that, there's also fluctuations in the frequency or the wavelength of the light. So you can do some fancy tricks, which kind of takes away the spread so that it's all the photons are pretty much exactly the same color. And what you'll find is that there's a quantum limit to how much you can reduce the fluctuations and the spread. And that quantum limit is because of when you get to counting photons, there's photon statistics. So the number of photons, there's an actual, you can't just, there's always a slight fluctuation. You can't say there are 10 photons per second and it never changes. That's not possible, because we have Heisenberg's uncertainty principle. That's where that thing comes in, basically. And so what it says is that there's always, you can never say for absolute certainty, you can never count your photons that accurately all the time. So what you do is there's a balance where you can only reduce the photon number spread, to a certain amount, and you can only reduce the kind of broadness, the different colors in that light beam to a certain amount, and that's a standard quantum limit. But that should give you the absolute best readout of that cantilever motion. So that's a quantum limited readout, if that makes sense. So that's just the signal that you're using to try and measure this motion. That signal is at the lowest noise floor that you can achieve, right? It's at a quantum noise floor. There's you can do what's called squeezing, where you decide, okay, we actually want to do better on the photon statistics, on the kind of counting side. We're happy to do that at the sacrifice of having a larger spread of wavelengths. So you can never get around the Heisenberg uncertainty principle, but you can kind of squeeze it so that one thing is more certain than the other. So you gain a little bit of extra precision in one quantity, but at the sacrifice of making it blurrier for the other one. Huh. So there's things that you can do to kind of almost get around, kind of go a bit more, but that's kind of the quantum limited readout side of things. So what I do is to say, well, how about if the cantilever is also quantum, because I'm extra like that. Because that's quite interesting too. And so what you find with that is if your object that's moving, if that is in a quantum ground state, well, the first thing that happens is you take away all of its Brownian motion, which is called thermomechanical motion. So this is what people tell you when you're at school. They go, solids are always vibrating, nothing is ever stationary, that whole thing. And that's what we're talking about. Everything that you see in front of you, even if it looks like it's not moving, it's definitely moving, but just on a very, very tiny scale. Everything vibrates a little bit. And that's caused by the fact that the environment is all around us. We're being bombarded with air molecules. They're imparting momentum to us. Even light, sunlight, photons have momentum. So, even that is a small contribution. And heat is everywhere. It's being transmitted everywhere. And heat is really the source of vibrations and stuff like that. So if you can stop those vibrations, as in remove them in some way, and you can do that through laser cooling, then suddenly you get to the 0 point energy of this cantilever, which means that it's pretty much the temperature of the mechanical mode is at close to I forgot what it's called now. The 0 point. No. Absolute, that's it. Gosh, like
absolute zero. Yeah.
Absolute zero. It completely left my brain, and I was like, wow, thank you so much. You reach nearly absolute zero. And basically all you're doing is you just need to counteract the vibrations. If it's doing that, you basically apply a force that kind of stops it from just doing that all the time. And what's really interesting is if you have a mechanical system that's in a ground state, you can put it into a superposition. So it can be in two locations effectively at the same time. And that's really important for doing very, very fine measurements of gravity gradients. You know, for example, if you have two cantilevers, or you have a cantilever in two different positions, up here and down here, if there's a gravity gradient, then you can perform matter interferometry, where you effectively, okay, I've used both hands, you effectively take you take the cantilever superposition state on the top and on the bottom, and because they're experiencing a different amount of gravitational force, they'll kind of, I don't know, one of them might move a bit more upwards, this one might not move so much downwards. So then you recombine them, you kind of put them back together, and it's an interference, but because they both experience different forces, you'll get a phase shift in that interference effect. It's the same thing as a Michelson interferometer, that adding the path length. So if you have two paths and you add a delay or a phase shift, you see your interference pattern like shifting in and out.
Yeah.
Wow, I'm really doing a great job with my hands. I never do this.
Jazz hands going on now. It's
jazz hands, amazing. I never thought that I'd actually be able to explain this properly, and I probably have messed it up. But anyway, so it's that, and what it is the fact that matter interferometry is so unique to quantum. You can't just take like two soccer balls or like one. You know, the first thing is you can't make a classical object in two places at once. That's the first thing. But to imagine having effectively an object kind of interfere with itself is so alien to classical physics, and that matter interferometry is so sensitive because it's inherent to the object. The object has been put into the superposition, it has to come back together. It's not the same as having two different objects coming together. It's so inherent that you manage to eradicate a lot of experimental errors, environmental errors, all this kind of stuff, because it's inherent to like the fundamental existence of this object. That makes sense.
Wow.
So quantum sensing, when you use both quantum limited readout and a quantum test mass, a quantum sensor itself, it really gives you access to mechanisms that just cannot ever be created in a classical way. That's why it's so interesting. However, it comes with so many challenges in how do you actually then perform these experiments, because it's so sensitive, then overly sensitive at this point. And it, you know, you won't be able to use those sensors for everything as well. They're not appropriate for all applications either. So for gravity sensing, absolutely. I mean, that will be transformative, you know, looking for holes underground, being able to know where to dig versus not to dig when you're doing construction, not bursting people's water pipes and stuff. You know, I can definitely see of use cases for that. But I wouldn't quite say that you're going to have a quantum navigation system inside a phone. I think that is where I start to personally feel that it's kind of just too much. But that's quantum sensing in a nutshell, I guess.
That's cool. Yeah, and it's interesting because so in the first season of these videos, I was talking to a colleague of mine, Shazia, who's working on quantum computing, and she said, you know, it's not going to be a mobile phone. I mean, apart from anything else, she's got the cooling and blah blah blah.
Yeah.
But okay, that's interesting. So, like you say, there's inherent challenges, but then there's also sort of the benefits. But then, so with your company, you're actually looking at sensors overall, and I guess you are looking at sort of more mechanical systems, more traditional systems. So what sort of things, so is this also, you know, is this for sort of transport and things like that? Is that what you're doing them for? What can you tell me about what it is you're doing with your company?
Yeah, no problem. So you know, I love quantum sensing and I'm a big advocate for it. You know, I still do a lot of work on quantum technologies for space, for example, and stuff like that. But what I found was I was already reading a lot about, you know, quantum applications, economics, you know, roadmaps for companies. I was kind of inadvertently having to read about a bunch of stuff to do with that anyway. Also, in my final year of my PhD, on a whim, I went for this Nature Entrepreneur First Innovation Forum.
Yeah.
Which was like a pseudo Dragon's Den, but with no money to pitch for at the end.
Yeah, but
I mean,
still.
still, it was a great experience, and this was very early on. I think this is kind of before the big boom in quantum startups. So this was 2016, I think, 2016, 2015. You know, that was like a 3-month intensive, you know, prepare a pitch deck, do some market research. I was assigned some mentors. And so that also was an intensive kind of, you know, looking into what a company is, what a quantum company should be, what the required funding is, what the steps are. And I just felt that there was this middle step that perhaps not everyone would want to do, but I felt it was important. And the middle step was optical sensing at a classical regime. So not going directly into look at my awesome quantum sensor, but actually, you know, what's an intermediate technology effectively?
Yeah.
What's a technology that enables quantum sensing, that shares similar components, that shares the same like thinking, the same type of systems engineering, but doesn't need to promise this quantum operation at the end. You know, it doesn't. It's not being sold on just it's quantum. It's sold as a proper commercial, marketable business proposition, right? Because what I felt was, as someone who had just finished a PhD where I didn't get to the quantum ground state, you best believe I had a lot of imposter syndrome around whether I should create a quantum company. Who am I to create a quantum company? And I've never even had a quantum object like my lab, right? I guess lasers are kind of quantum, so I'll give myself a bit of a
yeah.
But you know, so I also felt a bit of like, do I want to, because when you start a company, it's 10 years of your life that you're going to sacrifice, similar to doing a PhD and staying in academia probably. But I didn't want to do that again without a sense of not success. You can never guarantee yourself success, but a sense of, I think I'm doing the right thing and I think this is feasible. For me, in my level, you know, I'm not saying that people with quantum companies, you know, it's all a personal thing, right? So that was really important to me, that for me to kind of give up 10 years of my life to do a company, that I was comfortable with the expectations and what I can deliver. And, you know, I've had experience in industry. I've had patents before in industry, much more in this kind of classical sensing direction. And so it kind of made sense that, you know, all the little things that I'd done in my life, you know, were kind of showing me that I should go for this, but also all the bad things that have happened in my life and all the times where I've had to restart my work, or I, you know, felt as if other people were more experts, for example, in something or whatever. I also wanted to incorporate that thinking as well of, I want to feel ownership. I want to feel like I'm not just catching up to other people, that I'm always being left out of things. You know, I want to feel like this is my little corner. I'm going to fight for it. And classical inertial sensors just felt right. You know, in BAE Systems, I worked in the clean room for 6 months and we were building silicon gyroscopes for Segway. This is like ages ago. And being a part of that production line, it just made sense to me. Like, I already understand some of this chip stuff. I'm not the perfect expert of it, but, you know, why kind of risk everything on a quantum system that I haven't even got in my hands right now? All this experience that I could call back on. And yeah, it's not experience that I gained from academia. I think being comfortable in having multiple identities, that really helped. Being like, I'm an academic, but I also have this other part of me that isn't being utilized in academia, this innovation side, this all my experience in industry, the people that I know, that I've met who aren't quantum physicists, they're engineers or they're material chemists. I want to be much more flexible in who I work with. I don't want to just be stuck with having to be in this quantum space where you kind of feel a bit like, there's only a certain number of people that have the resources and the equipment to even do that. It's that kind of vibe. Yeah.
Okay. Yeah. And I'm sort of keeping an eye on time as well because I don't want to keep you too long, bearing in mind I've only kept you a while. So and that sort of leads on, I think, to something that you said earlier, was that you felt that the quantum sort of community is it's a community. It's a community. And you said that you felt more, you felt sort of like a new family, a new home when you sort of joined the Royal Academy of Engineers. It's interesting because so my last dealing with sort of engineering, the engineering world directly really, was before I started my PhD. So I'm talking 15 years ago. And I actually felt very much on the outside because the engineering side I was very, I'm a good engineer, I believe. But it was the equality and diversity side I felt that was lacking, the locker room banter. There was a lot of stuff that really made me think that I could never be an engineer because of what I saw going on around me. But you're obviously, you do a lot. We know each other through EDI work, and that's how we sort of know each other. And so if you're going into something like that and you're feeling comfortable and you're feeling like you've got a community, like I say, I'm looking at things probably 15, 20 years old. Do you think, is it a good environment in what have you seen?
Yeah, so I think this is quite dependent on my particular funder. I think that's the big caveat is
that makes sense.
Yeah, my entry into the engineering community has been very much, I don't want to say mollycoddled, but it's very much guided through the RAN rather than necessarily me cold calling, trying to get into it, if that makes sense, or through a course or through a collaboration with people that I didn't choose. Does that make sense? Or not choose, but when you're starting out in a community, you do kind of like reach out to lots of people and you don't quite know what to expect once you start working with them. But I didn't have that. I had the Royal Academy of Engineering kind of being that guiding point. So I think that's a big caveat there is it's really the structure of the RAN, I feel, that has helped kind of bridge that for me. I think the other thing is, STEM as a whole is so bad at representation and equity. And I don't want to get into kind of like, but physics is so bad and stuff like that, because I think we should all have ownership over this as scientists, not as a physicist and engineer, but as scientists, we should have ownership over the fact that science as a whole is not diverse, and it has major equity problems. I think for me, when I was doing physics, for example, I think it was something like 70 to 80% of the undergraduates were male at Imperial. And so I obviously immediately felt that sense of, okay, I think all the women on this course, you could fit into a tiny room, not even a big room, like not even a seminar room, a very tiny room, a bathroom probably or something, I don't know, just a very small space. I don't know how to describe it, but I felt that my perception of belonging got worse when I did my PhD. So I actually felt that my undergrad wasn't too bad. There was an overarching sense of, there's only a few of us, and there's barely any ethnic minorities on this course and that kind of thing. But in terms of my actual experiences, I had, when I was a teenager, I developed a really thick skin. So I think I brushed off a lot of stuff,
Mm.
you know, at undergraduate. It didn't ever reach a point where I felt that I couldn't handle it, if that makes sense. Although there was other stresses and issues and just pressure at being at Imperial that I felt were worse than necessarily how other people treated me. But when I got to my PhD and then after that, I don't know whether it's related to the fact that I decided to specialize in quantum. And I do think that quantum has this flavor. I cannot describe it, but you'd be surprised how, you know, even within the quantum label, there's a lot of like quantum information or quantum computing communities that don't even talk to the cold atom people. Or from my side, where, you know, my area is really new, which is quantum optomechanics. That's only existed in the last 10 years, 10 to 15 years. It's a very new kind of field. And you'd be surprised how disconnected we all are, even amongst each other, if that makes sense.
Mm.
I think that doesn't help. But also, I think as I started to do my PhD, that was really when there became a commercial edge to being involved in quantum. Like it really started to come out then.
Huh.
The UK National Quantum Technologies Programme, that's like over 6 years old now or something like that. I think it's definitely more than 6 or 7 years. But I feel like that kind of changed, not perception, but it, you know, whenever there's money involved and stuff, I think it always starts to taint things a little bit. And I certainly, there is this kind of feeling of capitalism and a feeling of an overhyping of things, and also a feeling of losing control, as in now there's a bunch of people who aren't necessarily academics at heart or whatever, don't know how to call it, but people that have different motives or who have come from different industries who perhaps don't understand the nuance that quantum technologies, I mean, historically, any work in quantum or atomic physics has always had dual uses, right? There's always been some ethics around stuff like that. And I feel like the flavor of how quantum is being seen, that's changed a lot over the last 5 years. And I think that's kind of brought about a different sense of, you know, how do I belong to this space? You know, I don't know how to describe it. I don't even know if I described it very well, but I think with engineering, there's always been a link to industry. There's always been a mutually beneficial link. There's always been a relatively safe link where people in industry will sponsor students, will sponsor research. The universities understand that. It's not always perfect. You get dodgy corporations, you know, sponsoring research, but it's open, it's transparent, it's at least understood. And I'm hoping even at undergraduate level that there is some discussion over industry or the perception that there's also industry for you. I feel like in physics, it's very rarely spoken about that your career may not be in physics at the end of it, or your career may not still be in quantum research. And there is a lack of this understanding of the relationship with industry or with finance, like, you know, startups and all that kind of stuff. And because there's that haziness, I always think that when things become complex, that people can't understand it. I mean, to me, that's the first barrier for equality, because just being able to understand something is a fundamental right. and when you're denied the information, or when it's not being shared equally to people, I feel like that may be happening in quantum tech. I mean, we're seeing that it's a national security thing now for many countries. Of course, not all information is going to be, you know, shared equally. So I don't know if that explains anything, but I guess that's my general feelings about why it's more difficult to necessarily feel that you can belong in the quantum sector. Yeah.
Yeah, it's interesting because there's so much fighting. I guess what you say about engineering always kind of being more application industry driven, and I think it's the same with material science as a whole. I mean, you know, half of my projects have been funded by companies. They just
Oh yeah,
they have.
awesome. Yeah.
So, that's kind of, I guess I've always had that. But then at the same time, yeah, if you want to get the money to do science, it's got to be sexy science. It's got to be something that sells. It's got to be something that potentially is commercial. And so, of course, people clamor all over it. So battery research and quantum.
Sure, yeah.
And I mean, I said I'm trying to put something together. It's because I've ended up working with a group who are making, qubits, and they need a material engineer, and it's like, oh, actually, this is interesting. This material science, no one's looking at it, and it's dead interesting. And then it's like, in the back of my mind, well, not even back of my mind, you're openly saying, and it's not blue skies research, so it's more likely to get funded just because it's a potential commercial thing. I know that there's companies I could speak to sort of partner up, and it's this scramble for funded in academia. I mean, it's bad. It's difficult. It's really difficult.
I mean, I love the fact that you automatically kind of have this feeling of, oh, I know companies that could help. Oh, I know, a direction and stuff. And what I find is, for a lot of quantum physicists, especially straight after a PhD, there is no roadmap that they can cling on to. Like, oh, I met that company and they can, they can probably help me stay on. It's always, did the PI win the £5 million grant? Because if they didn't, then I don't have a job anymore. It's always that hierarchy. Whereas, so I think I'm quite unusual in that straight after my PhD, I got funding from DSDL, because I knew that I wasn't going to be able to get funding from UKRI. So I went to industry instead. And that basically allowed me to make a prototype, and then the rest is history, effectively. That's effectively how I built up enough for myself to get my fellowship. But that's only because I worked in defense before, and I still had connections at BAE Systems, and I utilized that. But, not everyone gets to work in industry, come back to academia, and then feel that freedom of, oh, I don't need to beg, UCL or UKRI, I can go find money elsewhere. So, yeah.
I do wonder, though, and we talked before about how I think that, a sort of lab masters is, or fourth year is a really good thing. I mean, I did the same thing. We're talking in a similar way, and I worked in industry for 1.5 years. It wasn't quite as long as you, but we both did that. We both stepped away and then realised that we enjoyed the academic side of it. And I think that even though it was only a short time, it changes your outlook. It changes even just knowing how to talk to people and how to, I guess, just you understand where your research fits in the wider world, I think. And I think that I do wonder, you say that not everyone could work in industry, but I don't know, I disagree, and I almost start to wonder whether maybe more people should for a few years and see whether it's something. It's hard to step away because there's more. I was on way more money, but I do wonder whether it'd be a really good learning experience for academics to sort of at least just have that couple of years where you see where you fit into the scheme of things. I don't know.
Yeah, I mean, I would love for there to be a mechanism where it didn't feel so difficult to step away and then come. I think that's such a barrier for so many people of this, oh, I worked so hard to get into this university or whatever. If I take my foot off and I go and work in industry or something, that's it, I'll never have this door open for me again. And I felt that for sure. I was taking a pay cut. It was really weird. I was taking a huge pay cut, having to move from Bristol, which was lovely because my parents lived there. So I had it perfect when I was working. I had this big 1-bedroom flat with a garden, like the biggest space I've ever had for the last 10, 15 years. I had a really lovely life there. And I took a giant pay cut, moved back to Bristol to live in effectively studio flats to do a PhD. And it's still, even though I was giving things up, I still felt like I was like asking too much almost. That makes sense. I still felt like, oh, you're being so cheeky, like you stepped out for a bit. Now you think you're good enough to come and do a quantum PhD. Oh my God, Leah. I still felt that, honestly. And I don't know how we can remove that I think because PhDs feel very competitive, that's the first thing. I think,
Yeah.
I was lucky because my PhD was a department funded one. So it was a CDT nowadays where you have to get accepted into a cohort first, then you have to do like a year of labs again, and then you all bid for projects or you try and get a supervisor, right? I didn't have to do. To me, that almost feels a bit. I kind of wanted just to start a PhD. I didn't really want to have to go through another master's year, so I was quite lucky. All I had to do was interview with one PI. I didn't have to like join a cohort or anything like that, and I got hit the ground running as soon as I started. But I don't. That doesn't exist. That mechanism doesn't really exist anymore, where you can approach a PI and say, I want to do something, and they go, let me ask the department if there's any departmental funding. And no, you can't do that anymore because EPSA don't let you put in PhD costs into grants anymore. So yeah, it feels like it's gotten worse. Maybe not worse. Maybe the cohort system for CDTs is better because you let in more people together. I don't know, but I certainly felt that I was pushing it to even try and come back almost.
Yeah. I guess, my story is so different. I didn't even know what a PhD was. I went to industry and then I got offered one.
Oh, amazing. That's great.
But it was a different time as well. It was a different time. And it was because of my industrial work, because they wanted someone that could use the equipment and could build something because it was building technology. So, yeah. I realise I'm going to keep an eye. I realise it's sort of 4 o'clock, so I know that you're a very, very, very busy person, so I could talk to you for hours. And we did talk for an hour beforehand. We should have started earlier, and I should have pressed record. But with that, I want to let you go because I know that, like I say, you're a very busy person, so I just want to thank you so much. It's been a fascinating chat before and during the actual conference and during the recorded part as well. It's just been really interesting. So thank you for taking the time.
Thank you for inviting me on, and it's been an absolute pleasure. It's actually been the highlight of my day to do this because it's so rare that I get to just chat and it's not pressured in any way. So thank you so much, and I hope everyone's doing well out there in podcast land.
Thank you so much. Thank you again. So there you have it. That's there. I can't believe that I forgot to hit record. So basically we had 2 hours and we were chatting for 45 minutes and then I started recording and I just forgot to record. But we covered the same ground. It just meant that we were a little bit more rushed at the end. And that's totally my fault, but Liz, it was absolutely great chatting to them. It's interesting that there's certain ways in which we've shared a very similar path, actually, and we actually talked a little bit about that afterwards, off camera. So it was really interesting to hear her story. Just an amazing person, an amazing physicist, no two ways about it. She talks about having imposter syndrome, but no, she knows her stuff. She really does. She's good. She's not. She's where she is because she is good. So yeah, that was it. Hopefully you like this. Please like, subscribe, maybe follow Leia. And until next time, take it easy, and I'll see you soon again. Bye.